Hi you guys. So, really sorry I haven't posted something in a while. I've been really busy with work and juggling the demands of life. So this is problem 30 from chapter 9 on phasors. And so this problem you have a current source. It's 2 cosine 16E5 T amps. And it is in parallel with a 12 nanofarad capacitor, which is in parallel with a 100 ohm resistor. And this 100 ohm resistor is in parallel with a 60 ohm resistor that is in series with the 75 microhenry inductor. And we want to find this voltage here, the steady state voltage. So, the steps that you can do, the first thing you're going to do is simplify this circuit and not get freaked out by the existence of a sinusoid. It's just a parallel RLC circuit. So, like always, we simplify that into equivalent impedances. And you have a couple of tools. Notice that these are in parallel. You can collapse that into one equivalent impedance. And then once you do that, you have 2 choices in solving this problem. You can either use source transformation and then use a voltage division to find V out, or the way that I chose to do it is I collapsed these two into one equivalent impedance and found the equivalent impedance of the inductor, and then I used the node voltage method for finding V out because it's just going to be the voltage drop here. That's the way I'm going to show you guys, but I encourage you to, someone out there in video land, to try, please do it the other way and post your solution as a reply to mine, because I want to answer everybody's questions and I get hundreds of emails in my inbox all the time, and I can't because I'm just one person. So I'm really hoping someone will do a reply video with your solution to but not doing the node voltage way, but using source transformation. I would really appreciate that. Besides, your face is going to be cuter on the internet than mine. So, all right, pause the video, try it on your own, and let's get started. Here we go. So we have that circuit which we already talked about in part A. We would like to find the steady state voltage, or we're asked to find the steady state voltage. And in part B, we want to find out how many seconds or how much time the voltage lags the current by. So let's get started. Now, as I alluded to, I would like to solve this by simplifying everything into impedances. So let's go ahead and put our required formulas over here. So the impedance for a capacitor, I can never remember, I always have to look this up, is negative J over 2 omega C. And the impedance for an inductor is J omega L. Well, impedance for the capacitor is minus J over omega. Omega, the format of a sinusoid is cosine of, and then it's going to be something 16E5T plus omega. Or, excuse me, omega T plus a phase shift. So the omega in this case is right here. So we're going to go minus J. Let's just replace the parts here. So omega is the number that is the coefficient of time. And so that's going to be, omega is 16E5, and that's going to be times the capacitance, which is 12E minus 9. So once you put that into your TI-89, and obviously we use J in electrical engineering because I is for current, so on your TI-89 that stands for imaginary numbers. I'm sure you knew that, but you never know. That's equal to minus 50, or excuse me, the convention is to put the J first, minus J 50. And then over here, the calculation for in the impedance of the inductor is J omega, which is 16E5 times 75E minus 6, and put that into your TI-89, and you'll get J120. So capacitance of the, or impedance of the inductor is positive J120. So now we can replace this with its equivalent impedance. This is minus J50, and this here is J120. So now what I've got here then is minus J50 is in parallel with 100. So I'm going to simplify that. This is just a number, this is just another number. When you have impedances in parallel, it's exactly identical to resistors in parallel. So you can take the sum over negative J50 plus 100, or excuse me, 1 over 100, inverse of that, and that will give you the equivalent impedance, and that should be 20 minus J40 is what I got. So that's 20 minus J40. Okay, so now we're going to erase that and replace it with one equivalent impedance. Now I've got a current this is 20 minus J40, like that, and my current is going into this. And now I'm going to change this sinusoid into its phasor equivalent. So when you change it, only the phase angle matters, the omega no longer matters. So it's the magnitude of the sinusoid angle with the phase angle. So in this case, this phase angle, or the phasor for the current, is going to be 2 angle 0 amps. Okay, so I have 2 angle 0 amps going into here, right? And I chose to use the node voltage method. This is in parallel with this node right here, so therefore it is V out. Now I'm going to set up my node equations for this. So the first thing we need two equations because we have two unknowns. So node voltage at Vx. That equation is going to be current going in is negative minus 2 angle 0 plus this right here is going to be Vx over 20 minus J40 plus Vx minus 60 over, excuse me, Vx minus V naught over 60 is equal to 0. Let's group our variables together and put constants on the other side. Vx. Vx has 1 over 20 minus J40. And then it also has 160 plus 160. That's one equation. Plus V naught. V naught only has this, negative 1 over 60. Constants on the other side, the only constant I have is minus 2 angle 0. It's going to become positive 2 angle 0 over here. This is equation number 1 out of 2. So this is my number 1 equation. Now let's find our second equation by taking node voltage at V out. Okay, so node voltage at V out gives me V out. I want this current, and there's no current here because it's an open. So there's going to be two currents, this one. So V out, the current, this branch current is going to be V out minus Vx over 60 plus V out over J120, and those currents must sum up to 0. Now, for my second equation, I am going to put number 2 equation down here. Actually, I will put it up here because I'm not sure if you guys can see down there. Actually, I'm going to move this up here because I have a space problem. So, darn it. Okay, never mind, forget it, scratch that. I just hope that you guys can see it, but I'll tell you what it should say. So, with Vx, I've got negative 160 here and nowhere else. So my coefficient for Vx is negative 1 over 60, plus my coefficients for V out is going to be 160 here and 1 over J120 there. So 1 over 60 plus 1 over J120. And I have no constants to move to the other side, so that's just going to equal 0. So I have 2 equations and 2 unknowns, and I can solve that. So I always like to check to make sure my answer is right. If you own a TID9, which I'm sure you do because you're an engineering major if you're here on this channel, or just an epic nerd, I'm not sure which, there is something in AB, which is simultaneous equations. You go new and 2 equations, 2 unknowns, and then you put these numbers in just like regular numbers. So 1 over J, 1 over 20 minus J40 plus 1 divided by 60, enter, and then the next one is negative 1 over 60, enter, and then that equals 2. You have to, when you do phasors in the TI, well, I should say when I do phasors on the TI-9, I wrap them up in parentheses. Otherwise, I find that sometimes it doesn't work right. So 2 angle 0, which is actually really just 2, but just for completeness of the problem, we go 2 angle 0 degrees, enter. And then down here we have negative 1 over 60, enter, and then we got 1 divided by 60 plus, 1 divided by 60 plus 1 divided by parentheses, parentheses, J120, close parentheses, enter, 0, enter F5. And a lot of times I screw up typing in because I have parentheses problems. So let's see if I get the right answer now. And I do. So my answer is that Vx is, this is actually not that we were finding it, but this was this was, okay. So we weren't trying to find this, but we found it in the process, so I might as well tell you. This was 106.1 angle negative 45, and V out, which is the one we're really looking for, is 94.9 angle negative 18.4 degrees. Okay, so the answer to part 1 is the steady state equation for V out is, well, you don't leave answers in terms of phasors. You put answers in terms of sinusoid, and we always use cosine. So since our current was already in the form of cosine, our voltage will also be in the form of cosine. Now, so converting that into a sinusoid is pretty easy. The magnitude is the number before the angle, so it's going to be 94.9 cosine, omega doesn't change, 16E5t minus 18.4 degree volts. And, yes, that's correct. Okay, so that's part A. Part B is a bunch of definitions, actually. And conversions. It's basically a conversion problem. We need to know how many seconds this function lags this, right? It's behind by. It lags current, voltage lags current in this circuit by 18.4 degrees. And so that means that if you have current and it looks something like that, right? because it's cosine, and cosine starts at the maximum, and sine starts at the midpoint, right? So we have cosine, these are two cosine functions, and so it lags, so that means that the current is gonna hit this point faster than this one, so it's gonna be behind, right? So so this here is behind, this function is behind because it hits the same point in time later. So it lags, current lags voltage. But what is this 18? How does that translate here? This is the time domain, so this translates into some kind of time. And so the problem is, how much time is 18.4? How much time is 18.4 degrees in this situation? Well, I'm going to start by converting to radians. So, because omega is in terms of radians, so we have to do that conversion, because otherwise we're trying to compare degrees when the timeline or when the frequency is in terms of radians. So, 18.4 degrees. How many radians is that? Our conversion factor is, we have 18.4 degrees, and the conversion factor is 180 degrees for 2 pi radians. Oops, for pi radians. 2 pi is 360, right? So for pi radians. And my calculator gave me 18.4 is about 0.3217 radians. Okay? And then now, the second thing we need to do is we need to figure out how much frequency, how much radians there is in 1 second for this circuit. So frequency is 2 pi over, it's omega over 2 pi. And that is 16e. This is where the omega comes in. And so it's going to be over 2 pi. And that figure gives me there's 2.54648 radians per second. Okay? So now that I have that information, I can say if there's 2.46 radians per second and I have that many radians, how much time passed, right? So let's go back here. I don't have a lot of space on this board. So I have 0.3217 radians, right? And I want to know how much time it is. Well, if there's 2.54 radians per second, that's my conversion right there. So let me just check this, because I did it, let me just check, make sure this is correct, because I don't like to redo videos. Oh, come on, you piece of junk. Technical difficulties. Come on, you piece of junk, turn on. Holy crap. Okay, well, I was just about to take a detour, which I'm sure is pretty right, but can't confirm. Here we go. Okay, I'm going to stick with my original plan, which is the original way that I did that. I'm going to say, we know that time is 1 over frequency, and we have frequency, so all we have to do is just go time is equal to 1 period. This will give me 1 period, which is equal to 1 period, which is equal to 1 over f, which is 1 over 2.5464, and then now it becomes per second. So that gives me, what I got was 3.92699 microseconds. That's 1 period, so in other words, that distance is 3.969 microseconds. I can't believe my calculator crapped out on me when I'm in the middle of doing a video. Piece of junk. Come on. Okay, so now that we know how much is in one period, right? This is microseconds per period. Now we're just going to do the conversion to get there. So I'm going to erase this. I just erased the number of radians. Lucky thing, I worked this problem out first, right? So we want to know, we have 0.3217 radians in 18 degrees, right? So that's radians. And I wanted to know how much time. So I want to go from radians to time. Well, I have that much time per period, right? So I have one period, 360 per one period. Actually, you know what? I did this. Sorry, since I don't have a calculator, I can't verify. Okay, so then I want to do radians in one period. So that should give me 2.54. Okay, so we have to go to periods. Let's back up, y'all. Back up, y'all. Okay, so we want to go, since this is, the units for this is time per period, we need to go find one period, which is a full cycle. So we have 18.4 degrees, and there's 360 degrees per one period. And in one period is represented by time in 3.92699 microseconds. The period will cancel out, degrees will cancel out, and you will end up with 0.201 microseconds. So what that says is the current or voltage lags current by 0.201 microseconds. So that means if this is your voltage function, right, it's going to be, the current will reach, so current is actually ahead, so it's going to reach whatever point in time this is. Current will get there first, is what it's saying. So that time is represented by 200.201 microseconds. Okay, that's a wrap. Again, I'm appealing to all my watchers, YouTube watchers, to please solve this problem using source transformation or current division. I would love to see those as replies. Thanks.